you're having a great week and a great morning. And let's get this party started. Okay, here on the screen is the beloved map check. Here's where we are today. We're doing WeDrive on X and R charts. So that's what we're going to do today. We're going to work some problems together. And coming up on Sunday, we got a couple things due. One is the six-pack homework. That's homework 3 alpha. That's due by our normal time on Sunday, 11:59 p.m. on MyOps Lab. And then you also have another assignment that's been out there for a little while called the MRP Super B package. And that is on Canvas assignments, and you'll submit that on Canvas assignments. I'm not going to say both take a long amount of time, but you know how it is with MRP. It can be kind of tedious, slow is fast. So you might want to get started on those earlier than later, understanding that this is not the only show that you have in town. Looking ahead to next week on Tuesday, we'll go into the second half of statistical process control. That'll be P and C charts. And same, next Thursday, a week from today, we'll do a WeDrive kind of setting. Well, where we will go through some problems together. So 2 Zooms again next week. And then a week from Sunday, we'll have our last Pearson due. That'll be 3B and 3C, and that's on P and C charts. And those, all that stuff is open right now. So if you can work at your own pace, you can do that when you would like. Any questions about anything on the map check? Big or small? Okay, moving on. I am recording. I just want to say once again on class participation standards. And at the risk of sounding like a broken record, I'm just going to say this and I'm not going to talk about it anymore because I don't really like talking about it. So 2 weeks from tomorrow is when I will assess class participation. Obviously, many things have changed. So the short of it is class participation. Number one, you kind of got to show up to class to even begin having a conversation about participation. Beyond that, when you are here in class, I hate to talk about my expectations because it really should be expectations we have of each other. But I'll just say that I expect that folks have their video unmuted. That means I can see a moving picture of you, not necessarily a static image or a black screen. And of course, when I call on you to answer a question or to participate, then you're able to participate. If you don't have a working microphone, if you don't have a working camera, these are things that you probably need to talk to me about and let me know. It's not that you need to run out and buy a $300 microphone or camera. That's not what I mean. Otherwise, but what I do mean is if I talk about this and I continue to get a black screen, or when I call on folks, I kind of continue to get like yelling into the Grand Canyon, there's just this big echo and I get nothing back, then I kind of start assuming things that will just be reflected in my assessment of class participation. Okay, so that's all I really want to say about that anymore. If you have any questions about that, if you have any issues about that, please feel free to come up on the net and engage me how you see fit, and we can address those. I understand some people have limitations in connectivity and other equipment, and I'm very empathetic to that. But if we don't talk about it, I'm not aware about it. And again, my assumption goes where it is. It is what it is in this environment. I feel the need to talk about these things. In the classroom, obviously, things would be much different, but unfortunately, we're not in the classroom. So enough said on that. The other thing I wanted to talk about before we get started with the WeDrive today is I wanted to give another shot at explaining how to determine Z when we're doing these control charts, because I did not do a very good job the other day. And not only do I want to apologize for that, but I want to make it right. So let's just briefly talk about how we determine Z when we're determining on a control chart. So let's say here's our normal distribution. And again, all of our control chart theory is founded on the normal distribution. We have the mean somewhere in the middle here. And the whole idea of a control chart is we want an interval in which we want to capture performance. And we're going to cut that interval off at a certain point on the right and a certain point on the left. And of course, this is all symmetrical, meaning that if I extend this line out here like a greeting card, I can fold this thing in half and everything will fold completely on itself. What is the significance of that? Well, if I say, for example, that I want to capture 99.74% of the values around the mean, then this would look something like this. The first thing I'm going to convert that percentage into a decimal. Okay. And that also means that I'm not going to capture performance out here in these red areas. I am going to deem as out of control. Well, to do that, to figure out what that performance would be, I need to find out a value for Z that will go into formulas that I use. So to determine a value for Z using something like this, the first thing I need to do is identify the total of these two red areas. So in other words, I'm going to count values that fall in here inside of this area as being in control and values that fall out here as out of control. But I've got to figure out the Z, and that will help me figure out what this value and this value is. So to do that, to make this determination, it's actually really simple, or at least I'm going to try to explain it more clearly than I did the other day. The first thing I need to do is determine what is the sum of these red areas. So to do that, I'm going to take 1 minus the non-red area, and that's 0.9974. That difference is going to be 0.0026. All right. But I shouldn't stop there because that's the sum of these two. To determine one area and this value right here, I have to cut that in half. So I'm going to take that value and divide it by 2. And that's going to give me 0.0013. I'm still not done. Unfortunately, I have to take a 1 minus 0.0013 again to determine the Z value that corresponds with this line right here. And when I get that, I get a value of 9987. Now, there's two ways I can determine that Z value. One is I can go to the Z table, or the other is I can do this function. I think that's correct. And that should give me a Z value of 3. So either way, if I take this value and I go to the Z table, and when I say go to the Z table, I'm talking about the one that I've provided online, looks like this. And I would go find that 0.9987, or I can put it, I think I have the correct function, but I usually go to the Z table. Just that's my personal preference. Either way, I'm going to get a Z value of 3. And that is the Z value that I'm going to use in my formula. Now, on X charts and R charts, the thing is that to do an R chart, I have to use what I call the A2, D3, D4 table. And that chart is only built for 3 sigma, which is essentially this percentage right here, which gives me a Z of 3. So the short of it is, if I'm going to ask you to do both an X and R chart using the same data, I kind of have to make this my control chart limit, okay, within the construct of this class, because the table that you need to figure out the chart, the control chart for the range, is built on 3 sigma. Now that's not the case when we get into next week. So we'll talk more about Z, and during Pearson this weekend, you may come into some instances where it asks you to do something else with Z. But this is the short of it. Again, we want to identify the interval here. We want to take a 1 minus, and that 1 minus gives us the sum of these 2 tails. Okay, we've got to take that and divide it by 2, and that will give us one of these. And then we've got to do a 1 minus of that number that we divided by 2. That will give us this number here, this 0.9987. So you can't use this 0.9974 and go to the Z table. That would give you an erroneous value for Z. You have to figure out what the 1 minus is for that tail. I suppose you could do it here. It doesn't make a difference. If you did it for this tail, you're going to get a -3. You just can't use that in these formulas. And the reason that you've got to use a positive value for 3 in these formulas is because the formulas are built on a plus and minus system. So it takes that negative, essentially, when you do the minus portion and you keep a +3, it essentially is turning that +3 into a -3. It has it built in for you. However, if you try to use different values for Z, you're just kind of going to mess things up in the way the formula is built. Okay, so I, I I don't know how much of a better job I did explaining Z. I think I did a little bit better. Probably not a whole lot better. Any questions on this, determining Z? Okay, so with that, we'll go on into the We Drive for today. And let's see here. All right, so this packet you've got on your Canvas, I call this the sterile version because it doesn't have any of the guts in it. We're going to put the guts together today. I'm actually going to call on you and ask you to put the guts into it. I will try to be essentially just the cursor, and you guide me to where you want to go and what you want to fill in. And we'll go from there as if we were doing a U drive in our old setup. All right, so here's our first tab. And again, this is on your Canvas. If you want to follow along, I definitely encourage you to do so and populate these worksheets. I will post the solutions between today and tomorrow. So you'll have that to check your work, especially if you get lost along the way and you don't want to ask a question and all that kind of stuff. All right, so let's look at this first problem. I need to scroll down a little bit. This is called On the Nitro, named after my favorite drink from Starbucks. Sorry, Myra. It has less than like 8 words, but anyway. Okay, so Kenneth runs the local Starbucks, which is kind of an inside joke for me because the Starbucks I go to is on Kenneth Road. His regional manager has told him to validate that the drive-through is moving cars through at a consistent average with little variation. And he tells Kenneth to set control limits around 99.74% of the average performance. So there's that 0.9974 that we just messed with. So we know that we're going to have a Z of 3 that we're going to be using here. So during his coffee break, how ironic is that? Kenneth determines that the national drive-through standard deviation is 0.5 minutes. That means if he looks at all Starbucks and somebody has figured out that the population standard deviation is 0.5. Okay, so that's what that is. So determine the average drive-through processing time. What Kenneth does is he records 12 cars per each hour of his 10-hour shift and the respective sample ranges. So let's just make sure we understand what this data is. So during the first hour of a shift, Kenneth grabs 12 cars at random and records how long it takes them to go through the drive-through. And then he takes that average, and that is what that 3.9 is in this case. Excuse me. What he also does is he captures the range of that particular 12 cars. So the range, remember, is our maximum value and our minimum minus our minimum value. So for example, let's just suppose that in his sample, he had a car that went through in 4 seconds, and that was his longest car to go through. And then his slowest car to go through was 3. And all the other ones were between 4 and 3. Pretty tight group, probably pretty unrealistic. But regardless, we don't need to know all that. We just know that the range for that sample right there was 1. Okay, so I'm going to stop talking. Let's look at our questions. So let's just kind of scan them real quick. We have Q1 and Q2 and Q3, and they all deal with the mean performance of the drive-through. Okay, so just to give you a hint, that's going to be our X bar. We're going to be working with X bar to solve Q1 through Q3. So let's see who can get us started here. What do you think, Ames? What's one of the first things we should do here to get started?
To solve for X bar?
Well, let's see here. We want to do a control chart, probably, so that we can analyze and answer the question, is the drive-through mean performance in or out of control? And if it is out of control, what days is it on control, out of control? So you think we want to figure out what X double bar is? What should we do?
Yeah, I think we also need to find like the upper and lower limits of our control range.
Okay. So what should we do first?
I guess take the average of the average time to get X double bar.
Okay. So I'm going to get some space over here a little bit. And okay, so what should I do right here, Ames?
You just hit equals average and then highlight all the average time cells.
Okay. So that gives me the average of all the samples, which is also known as X double bar. Because any given sample, whether it's this one right here, or it's that one right there, or it's this one right here, that's all X bar. We could say X bar 2, X bar 6, etc. And the average of all of them is X double bar. Okay, let's hear from someone else. JT, why don't you pick it up? What's the next thing we ought to do here, or a next thing?
Well, the first thing I would have done, and maybe it is the next thing, is I would have made a plot so we can like see what's going on.
Okay, so what do you want to plot?
Maybe plot the control limits, like the average performance, the percentage. So we need to like say like in the middle we'd have 99.74%, and then we would have on the outside ranges our um, Z stat. So we need to figure out that.
Okay. I can go ahead. Yeah. So let's just go ahead and so we'd figure out that. I'm just going to throw in here that we figure out that is 3 because that's essentially what we just did. We've got 0.9974. Once the smoke clears, we're going to have a Z of 3. Okay. What do you think, Jasmine? What's another thing we should do to kind of get this party started?
Sorry, can you repeat the question?
Yeah. So we've determined what X double bar is. We've determined what Z is. We're going to use a Z of 3. We've still got these questions hanging out here. The overall thing we're trying to figure out is Kenneth's drive through. Is his mean performance in or out of control? And if it is out of control, what days was it out of control on? So we have a number of steps here. We obviously want to get a control chart so that we can analyze it. So what's one of the next things we should do to get that control chart up and running?
Um, Making like a scatter plot for like the
Say again? Can you say that again? So I think, Jasmine, your audio cut out. I think what you want to do is plot these right here and kind of just get our chart going. So to do that, I can highlight the time or I can just highlight these. Either way, I will get the same result. And I go to insert. Actually, I should be asking you all how to do this. And we get something like this.
I just have a question. How did you get 3 for Z? Did you just choose that or did it come from the data?
So the way that I get 3 for Z is I'm looking at that 0.9974. And that's this process.
Okay, that makes sense.
That makes sense. So that's
Yeah.
that 9974. And I think JT, that kind of addresses what you wanted to do. Okay. Is that good to go, Teresa?
Mm-hmm.
Okay. All right. All right. So back to this. So Tim, what do you think? What's something we might want to do now?
Find the upper and lower control limits.
Okay. How do we do that?
Take X bar plus and minus Z.
Okay. So so that would make this something like that.
Yeah.
Okay. Myra, what do you think? Is there anything else we need to do here with these control limits?
I thought you had to find the A2 and R bar,
Okay.
not
So
the Z.
yeah. So with this, we could do it one of two ways. With the X chart, since we have Z, we could use get rid of all this. So To find control limits for X, we could do one of two ways. All right, and we have some more stuff down here. Or we could do this right here. All right. So do you want to do this way, Myra?
That's the way I was doing it because you have to find the range stuff
Okay.
next later.
Okay. So what's something I should do next? I'm just going to zero these out for now.
Your R bar is your average of the range column.
So like right down here.
Yeah, at the bottom. And then I did the X bar for the upper. I did X bar plus your A2. That comes from that chart, the A2, D4, D3.
Okay. Which,
And you have to have your sample size, which I said was 12.
okay. So let me catch up with you. This chart.
Yeah. And then I went to sample size 12, and then I just took the A2, which was 0.266.
Okay. Anything
And
else I
then
need off that chart? Keep going.
well, later you will, the D4 and D3. I don't know if you want to do that now, but for the upper control limit, I did the X bar plus the A2 times R bar. And then for the lower control limit, I did X bar minus A2 times R bar.
Okay. So I'm just going to repeat what Myra said to do. We are using this formula right here. Okay. We could use this one, but the problem is when we go to do the R chart, we're going to have to use the sister of this formula, which essentially is what Myra is saying. So even though we know Z, the R chart can only be done with its table, which is built off of Z of 3. So we might as well go ahead and use this chart, which makes sense. So we're using this. We're going to build this formula. Actually, this should be a minus here, plus or minus, plus for the upper, minus for the lower. So we built that here, and I don't want to reference that. I want to reference that X, and then I'm going to go minus my A2, and then my little bitty 1.75, which I don't know why it's appearing so small down there. Get it bigger. And this is R bar. Okay, so now we have upper and lower control limits for our chart. Brett, what do you think excuse me, Brett. I'm thinking of your brother. I don't know why. I'm seeing you up on the screen.
Yep.
All right, so Ethan Locker, what's something we should do next?
So what I'm thinking is maybe instead of counting from 0 through 6 on our chart, we can change the axis or whatever,
Okay.
right? The axis.
I like how you're thinking. What should we change it to?
So I would say keep it between like 2 to 6 or 3 to 6 maybe.
Okay.
So we have like more variation on the chart.
This is great. So I'm going to just center in here so everybody can see what Ethan is talking about. So Ethan's talking about changing the minimum because we have all this white space here. And it's not really helping us see the nature of these changes. So if we change that minimum limit to 3, see how our chart changes? And that's what Ethan is talking about. And I like that because now we can see, okay, and those control limits are going to make a lot more sense. So other Ethan Green, what's something we should do now?
We could make a line across at the upper bound and the lower.
Okay. So I'm going to go up here. It doesn't have to be perfect. I'm going to crank that thing up a little bit. Okay. Is that kind of what you were thinking, Ethan?
Yeah.
And we can put another one. Down here. Okay. Any other lines we should put on here?
Should be fine, right?
Okay. What do you think, Josh? Should we add any other lines?
Yeah, I think we should add the X double bar in the middle.
Okay. Sounds good to me. And X double bar is just above 4.5. And we might want to, I like to just denote it differently so we can tell what we're talking about. Okay. What do you think, Gary? What other ornaments should we add on the Christmas tree here? Or on the tree?
Kind of like draw a circle and just outline which little marks are out of the I guess you could say out of bounds.
Okay.
So which ones are above or below the limits?
Okay, super. So let's start with the ones that are above. Now, we can do this a number of ways. We could just circle this. Let me just make a bunch of these circles so I have them.
Professor, these would be considered outliers, right?
Yeah, that's one way of putting them. They would be, when you say outliers, Luke, tell me, I'm not trying to play games. Tell me a little bit more about what you mean. I know what the word outlier means, but conceptually, what are you kind of getting at?
Yeah, there is a word that I guess like which day wasn't, or which I don't know.
Yeah, so let me answer. So let's talk about this day right here, day 2. Ellie, should we circle this day? This point here?
Yeah,
Why?
because it's above 5.015.
Okay. All right, Ellie is correct. We can know that by looking back at our table, and it's 5.3. Okay. So Luke, to your question, let me answer it this way and see if it's answering your question. The term outlier is often used with different kind of implications. In this context, it's a point that occurs above the upper control limit. Based on that single point alone, I would not declare this process as out of control. That hour on the second hour, I'm sorry?
No, sorry, it was just glitching in and out. My fault.
Okay. So here's the bottom line, Luke. That point is above the upper control limits. it alone does not necessarily make the system out of control. Somebody's got their mic on and just coughing into it. So
No, sorry.
So the point is, oftentimes we say, oh, this is an outlier, and we kind of dismiss it. I think to call something an outlier in this context probably might not be the best thing. I think what's better is to say a point is out of control and a system is either in control or out of control.
Right.
And the standard that we've established in our course here is that if we have 3 consecutive points out of control, then the system is out of control. So that's really a long way of possibly not even answering your question. Does that make sense?
Yeah, that was a lot of sense. Thank you.
Okay. All right. So what other points do we want to circle above this upper control limit? What do you think, Kyle? Are there any other points that we want to circle up here?
The very last one.
Okay. And why do we want to circle that one?
It's just above the upper limit.
Okay. So that's correct. That would be this one right here. Well, what about point number 9? What about that one?
That's within. That's within, so you wouldn't circle it.
So actually
Well,
that one is above.
I was looking at the chart. It actually is
Yeah.
above it.
So that kind of, this is a good double check here. And I just kind of threw this line here. And so to be precise, you want to make sure your values are lining up with your chart. And one way to continue to do that is do what Ethan had us started doing. Maybe we even go down to 3.5, and that'll get that much dispersion. But that's a good example where we don't want to miss those details. And then let's just double check this right here, 8, which is below. So we're not going to circle that one right there. Let's see. AJ, let's see. AJ's having connectivity problems. AJ, can you hear us?
Yeah, I hear you.
Okay. What points do we want to circle down here below the lower limit?
Well, didn't you just say it has to be like upper? So like the ones that are below you leave alone? Or does that not pertain to that, the lower ones?
So whether we're above or below, we want to identify when we're out of control.
Okay, so then you would circle hour 1.
This one right here?
Yeah.
Okay. Any others?
Hour 3.
Okay.
And hour 5.
Okay. Super. All right. So what do we think? What's the so what of all this? Trevor, what do you think? Is this entire process in control or out of control?
I would say it'd be a little out of control because there's more points outside of our lower and upper limits than there is in it.
Okay, so it's important for us to reflect here on our definition of in control or out of control. Kylie, what do you think? Is this in control or out of control?
I would say that it's in control because they're not in a row. So really it's just points that are just randomly out of control at one point. It's not really an issue that you need to fix because it's not 3 in a row.
Okay, so by the definition of 3 in a row, we would say it's not out of control, it's in control. But this here, and again, I will make it clear for you under quote exam conditions. This here is something we'd want to watch, because if we get one more point consecutively, then we would have a process out of control. Now let's just focus on these for a second when we look at Q3. So Teresa, what we have deviation here, and that's going to just happen. Okay. One car orders more stuff than the other car. One car orders one of these kind of Myra type of drinks that have like 8 things and needs a double shot of this and all this other kind of stuff. And then Gary just orders like something really simple, like a black coffee that takes him 2 seconds to fill. So we're going to have some normal variation here. But Teresa, what might be causing this? Because this is assignable variation and this is not normal. So what might be causing that?
So these are those separate hours or separate days?
So those are separate hours. Those are hours 9
9
and
and
10. Yeah.
So it could just be at the end of the shift, maybe somebody had to go home early, or maybe they're running out of supplies and everybody's getting tired. So they're just starting to have poor performance.
Yeah. That's really good. That's really good critical thinking. So those are great examples of assignable variation. People getting tired, running out of supplies. We could have a new worker that came on at hour 9 who wasn't as trained. Those are good things to think about assignable variation. And that's what I want you to think about when you think about assignable variation. Okay, let's go into the R chart. Whoops, I don't want to move that. That's the problem with slapping all the stuff on here is I can't move it as a group. So let's see here. Ellie, why don't you get us started on how do we do the R chart?
Well, just do the same thing with the range and graph it.
So you want to graph these points?
Yeah.
Okay. So I'm going to highlight those, go up here, grab what I call my connected scatter. All right. Okay. And Josh, what should I do next, do you think?
Since we already found our R bar, we can find the upper and lower level for the range.
Okay. So how do we do that?
Would we take we would find the D3 and D4 like Myra said, and use that to find the upper and lower level.
Okay, so let's do that. All right, so I have my handy dandy chart, and Kyle, which row do I pick from to figure out D3 and D4?
The right two.
The right two?
Yeah.
Okay. Which one specifically?
For which?
For how do I determine
Oh, which row or column?
Yeah, so for this problem that we're working, how do I figure out what D4 is?
Would it be 12? Row 12.
Okay. And why did we pick that?
There's 12 samples. I mean,
yep.
I think, yeah.
Yeah, so, okay, so let's be careful. Kyle is right. I want to make sure we got the right terminology. We have a sample size of 12. Okay. Each one of these, Kenneth took 12 cars. We actually have 10 samples. Okay. So remember, number of samples is not the same as sample size. All right. But bottom line is we do have an N of 12. And so we would go over and pick 1.716 for D4. And then I think it might be, let's see, 0.284 for D3. Okay. So Tim, what do I do with these values?
Would you do the same like you did for X bar, just plus or minus them with R bar?
Okay, so we're on the right track. My complement to this formula is this one. So for the upper control limit for R is going to be D4 times R bar. And my lower control limit for R is going to be D3 times R bar. So we don't want a plus and minus. I always like to think that D4 goes with the upper because it's bigger. That's my way of remembering it. But the point is, these formulas here are the counterpart to these formulas here, which are control limits for the mean. Okay? So we're going to take D4, multiply it by that value right there. And then we're going to take D3 and multiply it by that value right there. Okay, so same over here, and this is performance range. So I could steal these. I don't want to do that. All right. Luke, what do you think? Do I have any points out of control on my performance range?
No,
How do you know?
because neither of them are above or below the lines.
Okay. So Luke is correct. So if I look at these points here, and again, this looks like it's in control all the way down the line, pun intended. But I also want to double check and say, okay, my upper limit is 3.003. Do I have any values greater than that? No. Do I have any values less than 0.497? And the answer is no. Okay. So my process is in control for performance range, and for mean performance, it is, but I kind of want to keep my eye on this. Okay. And remember, the difference between the two is that my X chart, if I think this is the average performance, or at least what it's supposed to be, and I forget what we had, but what my X chart is going to say is if that mean performance is slipping. So for example, let's say that my drive-through time is actually getting greater, which means it's taking longer for cars to get through. My X chart should be able to pick up that this whole distribution has changed. Whole distribution has changed. And so, again, to reinforce how it does that is we take this red distribution, we turn it on its side, we line that up, and we determine these control limits. So when we have the blue thing going on, we see performance drifting outside of that control limit, which would be the same as performance out here. Okay, so that blue is actually going on right here, and that's why we have that performance up there. So that all is what an X chart does. In contrast, what an R chart does is an R chart, if red is kind of what we expect, an R chart tells us if this is going on, where we have a lot more inconsistency than we would like. So again, we do the same process and we tilt this distribution 90 degrees. Okay, conceptually, this is what we're doing. We don't physically tilt the distribution, but conceptually, that's what's going on. And so, if we had a range out of control, we would see wider and wider performance over time. So it's more likely that we would have points, out or above. It isn't always necessarily on both sides. We could have something like this, where we're inside the range there, but we're farther and farther outside here. Okay. So it isn't always that we're on both sides of the range. We could be outside the range on one tail versus the other. But this is our R chart. So we could have a process that's in control up here, out of control down here, vice versa, or it could be in control both mean performance and range, or it could be out of control on both. Okay, but that's what these control charts tell us. Okay, so this is important theory to know. Again, it's valuable to say, hey, it's out of control, but it's even more valuable to be able to interpret what that means. Okay. All right. Any questions on anything we just did so far?
I have a question.
Yep.
So like in the question, it like says the standard deviation. So do we just like ignore that since there's a range, or?
Yeah, so that's a good question. We don't have to ignore it. We could have approached this by using that standard deviation to figure out the upper and lower. And we could have used that to use this formula right here, which is, so to determine control limits, we could have used, because we know that standard deviation that's there, and we could have used that. Okay.
Okay.
As our Z still would have been 3, our standard deviation would have been that 0.5. This would have been the square root of 12. And this would have been whatever X double bar was. But we could do all that to determine upper, actually it's plus and minus, so we could determine upper and control limits using that. That wouldn't have been incorrect because we know the process standard deviation. I think the route we chose is because we were going to do an R chart anyway, and with an R chart, we can only use a Z of 3 in that set of formulas. So either way, we could have done it either way. Does that answer your question?
Yeah.
Okay. All right. Other questions on this problem? Okay. We probably have time for one more. So I'm going to go to the hardest one of the bunch. In the middle here is a problem about Batman driving the Batmobile out in the desert. So I would encourage you to do it on your own and then match it against the solution that I send you. But we're going to skip ahead to this one called Running Woman. And this is probably the hardest problem of the bunch because you've really got to kind of think about what the data is and what you need to do with it. So Coach Reif thinks that the 4x100 relay team has a shot at winning the Division III championship this year. He has 5 sprinters on the team. To assess the average performance and consistency of his team, each day at practice, he has them all run the 100-meter dash. And then he records their time for 7 days. So his log is below. And here's the 5 girls on the team: Jerry, Mel, Victoria, Melanie, and Emma. Coach didn't really pay attention during ops management. I mean, just that wasn't into getting mad skills. So he kind of takes our word for it, or somebody's word, that 99.74% control limits are fine. And in terms of these questions in the gray box, still the standard kind of questions. Is the mean performance of the team in or out of control? If it's out of control, on what days is it out of control? If it's out of control, what are some sources of assignable variation? And we'll stop there for now. So, but this looks kind of different. So, Myra, back to you. How do we get started with this set of data, do you think?
I just made the two other columns, X X bar and your range. And then for the X column, you just do the average of every girl on that day 1. And then I just drug it down to day 7.
Okay. So something like this.
Mm-hmm.
Okay. So it's important everybody see what Myra did. So Myra figured out, and I'm just going to speak for you for a second, but she said, okay, well, essentially, we are getting an average of all these runners. They're all running the 100-meter dash every day, and coach is averaging their times. And so that gives us an X bar for the day, which is 12.6. And then she just did the same process all the way down. Is that right?
Mm-hmm.
Okay. So with that, Kylie, how do we figure out the range of that day?
So what I did the math or the max function that they have on Excel. So max of all of the girls, so all of the 5 girls, minus the min of all of the 5. And then you can just drag that down.
Something like that?
Yeah.
Okay. And that works. So again, the definition of range is the maximum value in the sample minus the minimum value. Kylie used some Excel mad skills to make it easier on herself. You just as easily could have done it by hand and said, okay, which one is the largest? Entered that value. In this case, it would be Mel, and then minus by the smallest. And in this case, Victoria and Emma tied. So pick one, it doesn't matter. And 14.1 minus 11.9 is 2.2. Okay, so either way would have worked. So let's see. Now that we have the respective X bars, Ethan Locker, what's something else we might do?
Do we have to find X double bar?
Yep, we sure do. How do we do that?
So to find X double bar, we just take the averages of all the X bars.
Okay.
And that's your X double bar.
Okay.
Right there.
Super. All right. And let's see. Teresa, what's something we might want to do now?
Next we could calculate the upper and the lower control limits.
Got to spell them to do them. Okay. Sounds good. How are we going to compute that upper?
You'll compute the upper by, hold on, I lost my equation. Let's see. You will times x, or you'll do x double bar, or x double bar. Yeah, at the bottom, 13.
Okay.
And then you'll add A2 times R bar.
Okay. So how do I pick my A2?
Oh, you have to go to the chart to find that.
Okay. All right.
And I don't have the chart pulled up right now.
Okay. So I have the chart on the screen. Gary, how do I pick my A2?
Take your sample size, and from there you just go down the chart and find it. It looks like our sample size, if I'm counting correctly, is 5. So it's going to be 0.577.
Okay. Super. So it's going to be 0.577. All right. So I'm going to park. I don't know if I'm going to be using this space, so I'm just going to park my A2. While I'm at it, my D4 and D3 over here. A2 is 577. And I got to figure out what R bar is first. Luke, how do I figure out what R bar is?
Sorry, were you asking me?
Yep.
My laptop just died. I'm plugging it back in right now. I'm sorry.
Okay. That's all right. Ames, what do you think? How do I figure out what R bar is?
Take the average of the range column.
Okay. All right. And then back to, now that I have R, I have A2 over here. So back to Teresa's point, for the upper, I'm going to take A double bar. I'm going to add it to the product of A2 times R bar. And that looks right. And then I'm going to do A double minus the product of A2 times my R bar, which I don't know why it just disappeared. Why it did that. Something being funky. Let's just try it backwards. I don't know why Excel's being that way. Fine. Let's get some distance on the problem. We'll go over here. All right.
I think you want to minus it.
Yep, you are correct. Thank you. All right, super. Okay. Josh, what values do I want to plot? I got a bunch of values up here. Which values do I want to plot for my X control chart? my X bar.
You said which values do we want to plot?
Yep.
Um, would we plot? I guess like would we plot each day maybe possibly? So like day 1
Okay.
would be 1.
So I could plot day 1, and then which one of all these would I plot?
Wouldn't you plot all of them and then you would compare them to your X bar?
Yeah. So let's think about this. So I want you to look at these, and we have this X bar, and then look at our nitro. Here we didn't have all those individual values that went into making X bar. Okay. So these values here that I'm pointing out on the screen, these are X bars. The only difference between this problem and this problem is you had to determine the respective X bars. So the short of it is, for everyone, we're only going to plot these values here. Okay? Because otherwise our slide is going to be really noisy, and we don't need all this information anymore to tell us whether the process is in control or not. So we're just going to plot these, and we're going to do that by grabbing those and going here, and we're going to get that right there. Okay. I don't really want that 0 there, but I would probably go back later and clean that up. But I'm not going to do that right now. I don't know why that's there. Because it starts at 1, but regardless. Okay. So what I have in blue are only my X bars, the same way that here, what I have in blue is only my X bars. Okay. I'm going to put my control limits in. I'm just going to copy some from here. $16.5. So here I would have to adjust my chart axis anyway, because Excel's only taking it to 15.5. So I'm just going to put it at 17. I don't like that. And it adjusted my minimum value. Let's try 11. You know, that's don't really like that. Okay. And then my lower control limit is off the chart, so I got to adjust this again. It's going to go down to 10. Okay, so Ellie, is my process for mean performance in control or out of control?
In control.
Okay, because I don't have any points above the upper or below the lower. So it is control for mean performance for average performance. Now, Q4, as you look at this by yourself for now, it says, think hard and beyond the problem. Are the control limits possibly masking or an existing or emerging problem? So again, under test conditions, I'll make things, much clearer for you. But let's think about this. Look at these times. All right. So they're getting slower. And the reason they're getting slower is because of Melanie. Look at Melanie's times throughout the week. All of a sudden on day 4, she jumps from 14.5 to 17. And by the end of the week, she is running 25 seconds in the 100-meter dash, which probably most of you could walk faster than she's running. So something's going on there. And the point of this is an instance where having this wide of a control limit doesn't really make sense. Okay. So a wider control limit is not necessarily a better thing. If you really want precision, again, ideally, probably the Division III championship team, I'm just going to draw another line. They're probably running on average something that's much, tighter. So their average is probably around that X bar, which is here. Okay. So we look at over time, they're getting farther and farther away from that X bar. So yeah, they're still in control, but the bottom line is because coach didn't really understand what control limits meant, he probably set these control limits way too wide. Okay. Because at the pros, and many of you are athletes, and even those who aren't currently athletes, I think you all are smart enough to get this, that at the pros, the difference between winning and losing is probably a hair of difference. So in this kind of thing, coach probably would want to set control limits much more tighter. Okay. And so right away, he would be able to see, whoa, wait a minute, we are out of control here. Okay. So that's really what Q4 is about. Based on the control limits that coach set, the process is in control. But when we look at this kind of performance is not going to win the Division III championships. There is no flipping way. All right. And we're kind of running short on time, so I'm not going to go through it. You can on your own. I would encourage you to do the R chart. When you see the R chart, you will find that last point is out of control. And the reason that last point is out of control is that Melanie is driving that maximum value of the samples of each samples higher and higher. And eventually it causes the performance to be out of control for the range. And that's an example of what I talked about on the little drawing board there, where she's so far to the right that it's pulling the consistency of the team's performance out there to the right. Okay. So that's pretty much going to conclude our work for today. I will post the solutions to this later today. Any questions, big or small, on what we've done? Okay, super. As always, I will hang until you clear. I know there's a few folks that have things they want to talk to me about, so I will hang out for that. I will post the quote solutions to this later today. Beyond that, I'll talk to you when I talk to you, and have a great weekend. Take care.
Thank you.
Yeah.
Hi, Professor Chasky. Do you hear me?
Yes, I can. What's up, AJ?
All right. I emailed you. I'm not sure if you saw it, but I couldn't log in. My computer was frozen for a good half hour.
Okay.
So I was just letting you know I was having technical difficulties.
Yeah. I think Kyle or somebody gave me a heads up as well. So
Okay.
I appreciate you letting me know.
Yeah, no problem. I just wanted to let you know, and I wasn't just blowing it off. Don't worry. I was up.
Okay. All right. Cool. You getting all this all right?
Oh yeah, this is not bad at all.
Okay, good. That's a good thing. I'll take that.
Yeah, no, yeah. All right. Have a good weekend.
You too, AJ. Take care. All right, Miss Ellie, what's on your mind?
Well, I have two questions.
Only two?
Well, no, but just two different topics. Okay, the first one. If you always do an X and R chart together, then what's the purpose of the equation if you know the standard deviation? If you're gonna have to use the other one no matter what.
Yeah, I've had that conversation with my colleague, and I don't have a straight answer.
Because you get different answers for those two equations. Because I did the other one, and it's just different.
Yeah.
So.
So conceptually, I don't know. It kind of boggles my mind that we only have a chart that addresses 3 sigma. So
Yeah. But then the R chart doesn't even use the z-score at all. So
right.
What does it really matter?
What does it matter in terms of having the process standard deviation?
Yeah, like
it matters more on non-control chart type of things. So if we put control charts aside for a second, and I don't know how much you remember confidence intervals from statistics. If we know the process standard deviation, then let's talk about confidence interval real quick. A confidence interval is where I want to guess about the population. And so if I know the population standard deviation, then I can make a guess on the population mean in that interval. But quite frankly, it's probably less of a realistic situation unless I'm in a production situation. Beyond production, I can't think of why I would know a standard deviation when I wouldn't know the mean. You know what I mean?
Yeah.
And the textbook says this, so it's really kind of artificial. So I kind of feel bad because I don't have a straight answer, and I know you like those straight answers. My short answer, and I even feel embarrassed saying this, is, I mean, I wouldn't worry about it in terms of, the class. Beyond that, yeah, it doesn't make sense to me. If you're in a situation where you're doing control charts, I guess, one thing you could do is just not even bother doing a range chart, although that's kind of dangerous. Because you could have a process that's in control for mean and not in control for variation and consistency.
Yeah. So basically, you just want us to use the other equation with A2.
Yeah, that's kind of the Ellie answer.
Okay, that's fine.
I mean, I'm not here to play games with you guys. I'm not here to mess you up on purpose. It seems to me pointless, and I've had this conversation with my colleagues on this, and it kind of has gotten nowhere. I don't know why we have one chart when we're not just going to have situations with a Z of 3 all the time. But anyway, I think that's about a helpful on a scale of 1 to 10. I think that's about a 2. That's how what do you think?
It's okay. I
2,
mean, yeah,
3?
but I just know that I have to use the other equation every time, so it's fine.
Yeah.
Okay, now I have a question about this MRP thing.
Okay.
If I share my screen, will you be able to see it?
Yeah, I think so.
Okay, wait.
Let me do I need to shut off my stop share?
Oh my god, wait. It says host disabled attendee screen sharing.
Okay, stand by, I can fix that.
Okay.
Let's see here. I did this the other night for somebody. I just got to remember how to do it.